let's get started. For anyone who came a little late, I brought you a little early Halloween treat, so if you didn't grab some before, grab some on your way out. Please don't leave me with all this candy. All right, so let's continue. So last week, we talked about how we can improve the average memory access time when we're communicating between our processor and our memory by introducing a cache that sat between our processor and our main memory. Today we're going to change gears a little bit, but continue to think about how to keep improving performance, and specifically we're going to be focusing on how to improve the performance of our processor by introducing a new concept called pipelining. So, when we're building these systems, there's two main performance metrics that we care about. The first is latency. By latency, we mean how long does it take from when an input enters my system until its corresponding output is produced. The second metric is throughput. Throughput refers to how quickly is my system able to produce new outputs. Okay? So, depending on what my application is, I'm going to want to optimize for one or the other of these. Like, for example, suppose that I'm building, an airbag deployment system. What do you guys think would be the thing that I want to optimize for? Latency or throughput? Latency. Why?
You want to protect you, not deploy like a second later.
Correct, right? So what I care about is how quickly is that airbag going to deploy. I don't really care about it being able to deploy 10 times per second, right? How about, in my processor implementation? What do I care about there? Throughput. Why throughput? Say that again?
More computations, like faster, I guess.
That could also happen if just my latency is shorter, right? So what's my throughput actually giving me? They could be in parallel, but the key is that what I care about the most is how many new outputs is my processor able to produce per second. Okay, so that is, as you mentioned, throughput, right? So I'm not so interested in how long does it take me from when an instruction enters my system until it's completely executed. What I care about more is what's the rate at which my processor can handle producing results. All right, so let's start talking about the performance of combinational circuits. And we've seen some of this before, and this is a very simple circuit here. We've got an input X, which is being fed into these modules F, G, and H, which are all combinational. And what needs to happen is that first, F and G are going to produce an output based on this input X. And once both of those are done, then input H will do something with those two outputs and produce your final output, which we call P of X. Okay? So, when we talked in the past about combinational circuits, we talked about propagation delays, right? So how would I identify the propagation delay? What would it be for this circuit? In general terms, since I have no numbers on the slide. Anybody remember? Yeah.
Propagation delay of the critical path.
Of the critical path, and what's my critical path?
The path that takes the longest.
The longest, right? So my propagation delay is going to be the amount of time it takes me to get through the longest path. Okay? And so that's going to correspond to the latency of my combinational circuit. And throughput for a combinational circuit is simply 1 over that propagation delay. Okay, so let's take a little bit of a closer look at, how the modules F, G, and H are operating and see whether, we might be able to improve our performance. So here's basically a timing analysis. So if you have, your input X that's valid over here, and then it takes some propagation delay for F to compute its output, similarly for G to compute its output. Through the timing graphs, we see that in this case G is slower than F, but basically at this time over here, both F and G have their outputs produced, and so now H can begin doing its work, and it'll take another chunk of time, shown over here, until finally we have our valid output P of X. But if we take a close look at this, we'll notice that in this time right here, which is highlighted here in red, which is the time in which H is operating, what are F and G doing? Yep.
They're like sitting there holding their data.
Yeah, they're not doing any actual useful computation, right? So that's kind of wasteful, and ideally we'd like to have them do something useful. So what we're going to do is we're going to introduce registers into this combinational circuit. So these registers are going to hold the results that F and G produced so that H has them available, but at the same time F and G can start working on the next input that's coming in while H is doing some work. Okay, so let's analyze what happens now with this circuit, which we now turned into a pipeline circuit. Specifically, this is a two-stage pipeline circuit. So the F and G are going to operate in stage 1, and H is going to operate in stage 2. Who can help me figure out what my clock period for this pipeline circuit is going to be? 15? It's not quite 15. What else has to be true for our clock period of a sequential circuit? It has to, yeah? It has to be 25, that's right. It has to be at least as long as the longest register-to-register path to cover all of the propagation delays as well as the setup time. And so in an example, if we're going to assume ideal registers where the propagation delay and the setup time of our registers is just going to be considered 0, then all we care about is the propagation delay of the modules. And so we can clock this circuit here at a clock period of 25 nanoseconds. Okay? So if I can clock this at 25 nanoseconds, actually, before we talk about the pipeline circuit, let's just, for the numbers shown here, assuming these registers are missing, let's go through the latency and throughput numbers. So what would the latency of this combinational circuit be, given that F takes 15 nanoseconds, G takes 20, and H takes 25? 45, right? So it's just a path through G and H, which is my longest path, so 45. And my throughput, we said, is 1 over that, so 1 over 45. All right, so now let's get back to our pipeline circuit. So in this pipeline circuit, we said that my clock period can be as fast as 25 nanoseconds per cycle, right? And so how many cycles is it going to take from when X enters the system until P of that same X is ready? 2 cycles, exactly. So what is my latency going to be if I need to wait for 2 cycles? 50, because each cycle is going to take 25 nanoseconds, so my latency is going to be 50. So far, we've seen that in this pipeline circuit, my latency is actually a little bit worse than in my combinational circuit. But now let's take a look at our throughput. What's the throughput of this circuit going to be? Say that again?
1 over 25.
1 over 25, exactly, and that's the key, okay? And so even though it's going to take us 50 nanoseconds from when an input enters the system until its corresponding output is ready, we're going to be able to produce new outputs every 25 nanoseconds. Does everybody understand that? Terrific. So, of course, this is better, and so this is why, what we're trying to achieve by pipelining our circuits. Okay, so another way that we like to express what's going on in a pipeline circuit is using pipeline diagrams. And pipeline diagrams are basically, the way they work is the rows correspond to the pipeline stages, and the columns correspond to your clock cycle. So in order to express what it is that happens in the circuit that we were just looking at, what we would say is, okay, let's say just before, cycle I, my input x of I is stable. So now in cycle I, x of I is going to enter both my f module and my g module. They're going to do their work in cycle I. And then, at the end of cycle I, the f and g outputs are ready. So now in cycle I plus 1, H can operate on that initial input x of I. And then what we see here is that after 2 clock cycles, P of x of I is ready. Okay, so my output corresponding to that initial x of I input took 2 clock cycles in order to produce its output. Another thing that we see here is that for a particular input, we see it propagating down this pipeline diagram diagonally, okay? And so if we continue along this thought of, what's going to continue to happen as I work with this circuit for more clock cycles, basically what's going to happen is that while my H was working on x of I, my F and G started working on the next input, so x of I plus 1. And then in cycle I plus 2, H is going to complete working on x of I plus 1, and we'll begin the next on, and so on, okay? And so what we're going to see is this diagonal propagation through our pipeline diagrams. Any questions about that? Yes?
So here we have 2 stages, and we're doing this diagonal propagation. It takes like an extra, like the first stage, at stage I, H is doing no work, but for every stage after that, H will be doing work.
Correct.
So if we had like K stages, then for the first K steps, H wouldn't do any work, right?
That's correct. So
isn't that bad in a way too?
Well, it's only happening on startup, right? So you basically need to fill your pipeline, but once you've filled your pipeline, then you're going to be having a new output be produced every clock cycle, assuming there aren't other problems, which we'll get to later. Okay? Any other questions? All right. So let's first talk about some conventions. In order to be able to build pipeline circuits, what we want to understand is, first of all, what's a well-formed pipeline circuit? So a well-formed pipeline circuit is a circuit that has no cycles and that has exactly, if we want to call it a K pipeline, it's going to have exactly K registers from every input to output. Okay? And so if we think about combinational logic, we actually consider that a 0-stage pipeline. And we're also going to follow a particular convention which is going to allow us to put multiple pipeline circuits together so that they can work one after the other. And that convention is going to be that after every pipeline stage, we're going to have a register. So remember, we're going to do this on the outputs of each pipeline stage, not on the inputs. Why do we want to do that? Suppose that I have, here's one pipeline component, and let's say here's another one, and I want to now build a more complex circuit out of both of these. What's going to happen is I'm going to have a register on this output, another register here, another one here, and another one here, and this allows me to directly connect this pipeline circuit to this other pipeline circuit. If I also had a register on my input here, then I'd have, this extra register here, which isn't what I want. Okay? All right, so what about my clock period? We mentioned that the clock period has to be long enough to cover any register-to-register path for the entire propagation delay from the register through all the combinational logic, plus the setup time. Okay, so given that that's the definition of T clock, and a K pipeline has K registers or K stages in it, we now can also figure out what the latency and throughput for a K pipeline is. So specifically, the latency of a K pipeline is going to be K times our clock period, and the throughput is 1 over T clock. So you notice that the throughput actually doesn't depend on how many stages we have. Okay? All right, so let's take a look at an example of an ill-formed pipeline. Let's try to figure out, what's wrong with this picture that I'm showing you. Why is this not a good pipeline? Any ideas? Yes?
The register in front of the
It could be, but I might have a reason to do that. So assuming that it's still okay for it to be there, do you see anything else that might be wrong? Yep.
Some paths have 2 registers and some have 1.
Exactly. Okay, so what are going to be the implications of the fact that I have a different number of registers along the different paths? So specifically, first of all, I can't give you any value of k for which this is going to be a valid pipeline. Okay, so why is that? Because if I look at my path from x out through to c, I go through 2 registers. If I look at my path from y out to c, I also go through 2 registers. But what happens when I follow this third path, which goes through A, B, and C? Now I've only gone through a single register. So what are the implications of this? The implications of this are that this module B here is getting inputs from 2 different, they're mixed basically. So it's getting, let's assume, we started with x of I and y of I in my first clock cycle. Okay, in my next clock cycle, y sub I made it over here, but now I have x sub I plus 1 working through here. So that means that B is going to see on the x side an input that corresponds to time I plus 1, whereas on the y side it's going to see an input that corresponds to time I, and that's not the behavior that we're trying to achieve. Okay? So by making sure that we always have the same number of registers on each path, we'll guarantee that we're not mixing these inputs from different time periods. All right, so now what we're going to do is we're going to define a pipelining methodology. Basically going to give you a set of rules to follow in order to take any combinational circuit and pipeline it. Okay, so here's our combinational circuit that we want to pipeline. And the first thing that we're going to do is we're going to draw a line that crosses all of our outputs. Okay, so here we have a single output, and so I'm going to draw this one line, and I'm going to label the 2 ends of that line as my terminals. Okay, this red line here we call a contour. It represents a stage of my pipeline. Okay. Now, I'm going to continue to draw these contours crossing through my circuit, and I'm always going to connect these 2 red endpoints. And the one thing, though, that I have to absolutely make sure is true in order to end up with a valid pipeline is that any time that I cross through some wires in my circuit, it must be the case that that the wires cross this contour or this boundary in the same direction. So what does that mean? If I look here, if I label, let's say I'm looking at this contour right here, the second one I just drew, and I label the left side my inputs and the right side my outputs, it must be the case that every arrow that crosses this contour is going to go from inputs to outputs. Okay? So if you have some funny shaped circuit with arrows going in different directions, your best bet is always to try to redraw it so that the arrows are all moving in the same direction, and so that way when you try to pipeline it, you don't end up producing circuits that don't work. All right, so then let's say, I go for one more path through my circuit, and let's say that this is my pipeline circuit, okay? Now, what about registers? The way that I know where to put registers is I basically place a register on every single intersection between my contour, which corresponds to my pipeline stage, and a wire that I cross. Okay, so every one of these blue circles corresponds to a register, and you'll see now that no matter what path I follow, I have exactly 3 registers from input to output, right? So I have 3 registers if I go this way, I have 3 registers if I go from here, and so on. Okay, is that clear? Yes?
What's the intuition behind the way we draw these lines and why they make a valid K pipeline, and what's the standard way of doing this without fault, I guess?
Yeah, so we're getting there. So this will give you a valid K pipeline, but now we want to try to analyze, what's the performance of this pipeline that I just created here, okay? So specifically, if I tell you that this is my pipeline circuit, who can tell me what the T clock for this circuit has to be? What's the minimum T clock? Yes? 8. Where'd you get 8 from? Because C has a propagation delay of 8, okay? So that means that every clock period is going to take 8 nanoseconds. And so if my clock period is 8, what is my throughput? 1/8. And what's the latency for this particular circuit? How many pipeline stages do I have? 3. And so what's the latency? 24, okay? So, yes?
If 8 was 5, was 6 nanoseconds, would the clock still be 8 or should it be 9? Because I should consider A and B a single thing, because they're both set for a register.
So if C was 6, then, sorry? If C was 6, then what I would have done is that I would have created another pipeline stage that separated A and B, okay? And the reasoning for that is as follows. Basically what I'm trying to do is I'm trying to isolate my slowest component, okay? So that there's nothing before it or after it in its pipeline stage. So if I look at C here, which is my slowest component, it takes 8 nanoseconds. It's okay for it to be in the same pipeline stage as D and E because D and E are operating in parallel. There's no relationship between C and D and E. Okay, but what I wouldn't want is to have picked, B to be inside the same pipeline stage, because then that would mean that my T clock would have to be 11 nanoseconds. Okay, so to go back to your question, if instead of being 8 nanoseconds as my longest time period, I had 6, I would want to make sure that I didn't create another path which was longer than 6, because that wouldn't give me the maximum throughput. Does that make sense?
But if C was 6, the clock would be 7 because of A and B.
If I didn't change the picture, then yes, the clock would be 7.
But that's not about B.
Yes. So, sorry, I should have answered that directly. Yes?
How does, if you're given the circuit, how do you decide, what the number K is? How did you know to only draw 3 lines versus 2 versus...
So, you basically have to try to figure it out the first thing you're going to do is figure out what's your slowest component. That's going to determine your T clock. Okay, then depending on where that slowest component sits, the fact that you're isolating it, if it's somewhere in the middle, that means I'm going to have at least 3. And then if it turns out that after, isolating the slowest component, I still have some combinational paths that are longer than that slowest component, then I would continue to add additional paths in order to make sure that no path is longer than that slowest component. Yeah?
But is it impossible to give you more advantage? Not tracing a new line and leaving those 2 guys that take longer than the longest components together. Can't it be more, give you more advantage?
I'm not sure that I followed that question, but I just want to make sure we don't get too sidetracked. So you're going to get a lot of practice with this in tomorrow's recitation, okay? So the key is to keep the following in mind, okay? The first thing is, when you're doing this, you have to create a valid K-stage pipeline, meaning you have to have the same number of registers along any path. We're always going to start by putting a register through all of our outputs. That's the convention that we're following, is that all outputs of each stage always have registers on them. And then you're going to try to isolate the slowest component so that your T clock is no longer than that slowest component, okay? And then after that, you'll basically add enough contours so that no other combinational path is longer than that slowest component. Yes?
So why did you not draw a line between D and D and A and B?
I could have. So there are certainly other valid ways of pipelining the circuit for the same performance with regards to latency and throughput. Okay? All right. So now let's take a look at another example. Yeah?
The clock is always the thing we want to reduce at max.
Say that again?
The clock is always the thing that we want it to be as lowest as possible.
Yeah, because our latency is always going to be T clock times the number of stages that we have. Okay. Well, actually, sorry. I will say that's not 100% true. We'll actually see in this example in just a second, which is if I end up producing too many pipeline stages, that might not be, no, sorry, you always want the t clock to be the minimal because all the other ones are going to have to be just as slow as it. So, sorry. Okay, so let's go on to this circuit. So here we have a circuit consisting of A, B, and C, and the latencies of each of these modules are 2, 1, and 1. All right, so in a combinational circuit, which is what we call the zero pipeline, the latency of the circuit is the longest path, which is how long? 4, right? So if I go through A, B, and C, I have 4, and so my throughput is 1/4. If I now want to turn this into a one-stage pipeline, all I do is I put a contour on my output, and does that change my latency and throughput? No, right? So my latency and throughput are still 4 in the one-stage pipeline, okay? Now, what if I put a second contour through this circuit, okay? When I put the second contour, I wanted to isolate my A component, which was my slowest one, right? So now, what's my clock period? 2, and how many pipeline stages do I have? 2, and so my latency continues to be 4, it's 2 times 2, but what's my throughput? It's 1/2 because my clock period has gone down to 2, okay? Now suppose that I went and I added yet another pipeline stage, this one here labeled 3, now what's going to happen? I have 3 pipeline stages, what's my clock period? It's still 2. So what's my latency if I have 3 stages and a clock period of 2? It's 6. What's my throughput? 1/2. So what happened here? I just added a pipeline stage that didn't actually help me. Okay, so it is possible that if you add too many, you're going to just increase your latency without improving your throughput. Okay? And the last point I wanted to make is that it is possible to end up with back-to-back registers when you go about pipelining your circuit in order to make sure that you're producing a well-formed pipeline. So don't be surprised by having one register followed immediately by another register without any combinational logic between them. That's perfectly valid if the reason that it's there is in order to ensure that every path from input to output has the same number of registers. Okay? All right, so in the previous example, the best I could do in terms of my clock period was 2 because my A module took 2 nanoseconds. So what's another way that I could try to improve this system even more? What I could try to do is find a pipeline version of A where I have, a 2-stage version of A, each stage of which takes 1 nanosecond. Okay, so A, the latency of A is still 2 nanoseconds because I have to go through both of those stages, but now I'm able to run my clock at 1 nanosecond. Okay, so what are the implications of this on the pipelining of the circuit as a whole? Is that going to help me? Yes, because now what I can do is I can produce a pipeline that looks like this, very carefully making sure that my contours pass through these registers of my A, which is a pipeline circuit, and also carefully making sure that these same contours that pass through A also cross any other wires in my circuit so that I end up with the same number of registers again on each path. And so what I've ended up with now is a circuit that has 4 pipeline stages. And what's my clock period though?
Just
1. Okay, so now my latency is once again 4, but now my throughput is just 1. Okay, so so I was able to improve my my throughput by replacing that A component with a pipeline version of that A component. Okay?
Good question.
Yeah.
Used on composition convention. So you have you're saying that every register has a register on output?
Yeah, so this is what I was trying to show here. It's a little hard to show with basically, so this, if these are your modules, at every stage of my pipeline, I'm going to have a register which corresponds to, that separation between the stages. So I could have something, that looks like this, where this was just, each of these things was a one-stage pipeline. But then I can combine them because I have a register at the output here. And so if I put these together, let's say that the T clock of this, was 4, and let's say the T clock of this was 5, I'm able to, because this register is here, compose these and now have a larger circuit whose T clock is 5. Okay, but they don't add up because of this register right here. Okay?
If you had a register before C, like you had before, then you could consider that as a three-stage.
Yeah, if I had another register here, then this becomes a 3-stage pipeline. And so that's just increasing my latency without helping. So it wouldn't be invalid, but it would just not be as efficient. Okay? All right, so we have a few alternatives when we come up to thinking about, how do we want to pipeline our circuit. So aside from following, the methodology that we mentioned, we want to make sure that you understand the trade-offs between these 3 different approaches. Okay, so what's shown here? In the top approach, so what we're trying to do is we're trying to have an input go through 3 modules, F1 followed by F2 followed by F3. And in my first approach, I'm going to say, well, let's let all 3 of these modules can live in one single pipeline stage. Okay? So I have a pipeline register, ultimately when I'm combining this with something else that starts before my F1 and ends after F3. Okay? Now an alternative to that would be to say, well, I could get a better T clock if I put each one of these F modules in its own pipeline stage, okay? And so that's what model B is showing us, where F1, F2, and F3 are each in their own pipeline stage. And then the third one is showing a situation where we're actually implementing a folded implementation of this circuit, where we're making use of this Fi module to implement all 3 of F1, F2, and F3, okay, assuming that there's some commonality between them. And the way that we're using them is you go through F of I 3 times in order to get the same effect of having gone through F1, F2, and F3, okay? Is everyone clear on those models? So now what we want to do is we want to think about, what's the behavior of these different models. So if you saw, let's just actually backtrack this and do it one more time. So in the first one, what's going to happen? An input comes in, and it's just going to go through F1, followed by F2, followed by F3, and it's not going to stop until it gets to that output register. Once it's done with that, then I can have another input coming through this pipeline stage. So in this model, this first one, where I have all 3 of my F's together in one pipeline stage, I cannot put something into F1 before my first input made it through all of my F's. Okay? So only when this red dot exited the entire pipeline stage, now it's okay for me to pass a new input through F1, F2, and F3. Okay? So that's the first model. What's the second one? The second one is every single module is in its own pipeline stage. Okay, so now I have this red input, and as soon as it goes through F1, I'm now able to put something new into F1. Okay, so this red thing is now going to go through F2, while green is going through F1. And now I'm going to have 3 things operating in parallel, okay? So one in each one of these modules, and so on, okay? So that gives you a sense for the difference between how things propagate through the top and the second one. Now what about the third one, okay? I'm still trying to implement something that has these 3 functions, F1, 2, and 3. Okay, so in the third one, what I've done is I've reduced my area by just having one copy of F. But now that what that means is that I'm sharing F amongst F1 and F2 and F3, so I can't do them all at the same time. I still have to do them in order. And so what that means is that when an input comes into this one, it's going to go through Fi, then it's going to go through the register, which will hold, the result it produced, and it'll go through again 2 more times in order to effectively do F1, F2, and F3. And only after I've gone through my folded circuit 3 times can I then pass a new input into this pipeline stage. Okay? So does everyone follow the difference between these 3 models? Yes?
How does Fi know which one of F1, F2, and F3 to become?
You would have internal state within the F module that has that smart. So you might have, a state register that represents that. Right? Like, for example, I don't want to confuse you more, but like when we built a fast GCD, we had like 2 copies of our GCD and we had a little state register that picked between them, so something like that. But the idea here is that most of the hardware is shared, and then there might be some pieces that are different, but that's all within F of I, so you don't have to worry about that.
And what is the mux selector doing? Like, is it always the same value, or is it?
The mux selector is determining whether you're starting a new pipeline stage, meaning that you're taking a new input in, or you're in one of your intermediate stages. So if you just did F of 1, then your input's going to come through this input of your mux, and then you're going to do F of 2, and then F of 3, and then you'll be ready for a new input which uses the top input of the mux.
So the selector also depends on some state aspect of that line, right?
Yes.
Okay.
Okay, any other questions? Okay, so what we want to do now is analyze basically the difference between these 3 types of implementations as far as what their effect is on clock period, area, and throughput. Okay, so let's start with the clock period. Which one of these is going to have the slowest clock period? You think 2? 1, right? Why 1? Or A, let's say? That's right. I have to have a T clock that's going to allow me to do F1 plus F2 plus F3 all in the same clock period. Okay, so the relationship of the clocks of these 3 different models is going to be that A is the slowest, and for B and C, they're approximately the same. They're basically, who can tell me actually, why are they approximately the same? Ignoring the delay of the multiplexer.
Because every time we're done with F1,
Well, in B, basically, what would my clock period be? It would be dominated by the slowest one of F1, F2, and F3. Okay? And so the idea is that F of I would also be basically dominated by that slowest one. And so T clock for F of I would be equal to T clock of the maximum of F1, F2, or F3. Okay? And we're just, assuming for now that amount of time is much larger than the delay of this multiplexer. Okay? All right, how about area? Yes?
I thought it should be like 8 because you have to wait for it to do the 3 computations before some.
That's right, but that doesn't affect the clock period. That's going to affect the throughput, which you're going to see in just a second. Okay, so the clock period is still, how fast can I run my clock? I run my clock in the amount of time it only takes me to go through F of I once. Okay? Any other questions? All right, great. So what about area? Which one is going to be the best for area? C, right? As we expect, because we only have one F of I. And what about the relationship between A and B? B doesn't have registers, right? And so, A doesn't have registers, so its area is going to be less than B. Okay? All right, what about throughput? So I've put this answer here. So who can explain to me why this is the relationship of throughput? So first of all, which one has the best throughput? B. Okay, so B is like our regular pipeline situation. Okay, which one's going to have? What's going to be the difference between A and C? Why is A's throughput actually potentially better than C's throughput? So think about the fact that in C, we have a clock period that's dominated by the slowest of the three components, and we have to go through that portion 3 times. So basically, we can only produce an output once every 3 clock cycles, and that clock cycle is dependent on the slowest one of these. Whereas in A, our clock cycle is just the sum of F1, F2, F3. And so if F1 and F2 are much faster than F3, then that clock cycle of A is going to be less than 3 times, the slowest component, which is what's going to happen in the throughput for C. Okay? So I'll let that sink in, and if you have questions, we can talk more about that later. Okay, so now we want to move on to pipeline processors. So we talked about combinational circuits, and we want to now talk about, well, how are we going to pipeline our actual processors? And so when we think about pipelining our processors, we think about how long does it take us to run a program. And in order to figure that out, we basically have these 3 parameters to consider. There's the instructions per program, the cycles per instruction, and the time that it takes to run a particular cycle. So in order to improve our time per program, we could try to change any of these 3 parameters. So if we executed fewer instructions, then that could be helpful, but that probably means that we have to introduce some more complicated instructions into our instruction set architecture, which would then affect our clock period. And so, for the sake of this discussion, we're going to assume that we're not going to do that our ISA is fixed. So the other 2 things we can do is we can try to reduce the cycles per instruction, or we can try to reduce our cycle time. So if we take a look at our single cycle processor, right, this is a picture you've all seen before. How would I go about figuring out what my clock period for the single cycle processor is? Well, I have to allow enough time for every single, piece of functionality. And so what does that mean? Specifically, let me just skip for a second here. Specifically, what I have to have in my clock period is enough time to fetch my instruction memory, to do my decode, to fetch my registers, to execute, to potentially go to my data memory, and then to write back my results. Okay? Now, my CPI for this processor is 1, because we said it's a single cycle processor. And T clock, as I just mentioned, is basically dominated by the longest path. So regardless of which instruction I'm executing, whether it's this one in yellow, which is an ALU instruction, or this one, whoa. What just happened? Or this one in red, which is a memory instruction, I'm going to have to make my T clock long enough to allow for the longer path, which is the one that includes going through the data memory. And so that's kind of wasteful because every single time I do an ALU instruction, I actually have to allow enough time for my memory, even though I might not be using it. So what could we do instead? Well, ideally, what we want to do is we want to keep our CPI equal to 1, meaning that we are approximately, completing 1 instruction per cycle. But what we want to do is we're going to improve our T clock by splitting up our data path into smaller chunks so that T clock is not so bad. And so what we're going to study in this class is what's called the classic 5-stage pipeline, and it consists of the following 5 stages. The first is instruction fetch. So first you fetch your instructions from your instruction memory. Then you decode your instruction, and from the decoded instruction you figure out which registers to read from the register file. Then you go to your execute phase, where you're going to actually take the contents of the registers you just read, perform some operation on them in the ALU, and produce a result. Then you're going to go to your memory stage. So if you have a load operation, what you produced in your ALU would be the address of that load operation, and then you would actually go and do the load in your memory. And finally, you have your write back stage. Okay? So what would happen to the T clock if this is a situation where each one of these is running in its own pipeline stage? Now my T clock just has to be the maximum of one of these stages rather than the sum of all of them. Okay, so I'm going to be able to make my T clock much, much better if I can divide my processing into these 5 different stages. Okay, so you might say, well, even though I'm a little over time, but you might say, well, okay, well, why am I not just done? And, we don't need to have 4 lectures on pipelining. All I have to do is, create my 5 contours, and I've got here my fetch, my decode, then my execute, then another stage, which is my data memory, and finally my write back. Okay? Well, it turns out that this is not a combinational circuit, right? So it's not quite as simple as just drawing those 5 contours. So there's 2 things that are going to produce problems for us here. The first is that we have state, okay? So we've got our registers, we've got our PC, we've got our memory. All of that is state. So we have to pipeline this a little differently from what we did with our combinational circuits. Okay, the second thing is that we have some loops related to the reading and writing of our registers, right? If I look over here, I'm reading a register and I'm also writing to a register. Now, if I'm going to have one pipeline stage reading while another one is writing, I might have some dependencies because I want to read the result of an instruction that might be further down in my pipeline. Okay? And so we have to figure out how to deal with these kinds of issues when we're pipelining our processor. So let's see what we're going to do. So specifically, to kind of summarize the 2 types of issues that we just mentioned that we have, in the case of, where one instruction needs to read the results of another instruction, that's what we call a data hazard. In the case of, I guess I didn't actually show this here, this other loop here, which is that we update the PC to go someplace else, meaning we did a branch or a jump or something like that, that's referred to as a control hazard, okay? And so our pipelining methodology for our processor is going to have to be a little smarter than just dividing up these 5 stages. It's also going to have to deal with data hazards, and it's going to have to deal with control hazards. So the way that we're going to do this is we're going to first, figure out, well, how do we pipeline a simple processor that doesn't have any of these hazards and that doesn't have, any dependencies between the instructions. And then we're going to figure out how to augment that in order to handle data hazards, and finally how to handle control hazards. So today we're just beginning the very simple part of it, which is how do we handle the situation where we don't have any hazards, as well as, getting to a very simple handling of some data hazards. And then next lecture we'll cover the rest of that. So here's, my processor redrawn, and basically I've separated out, vertically the 5 different stages that we talked about: the instruction fetch, decode, execute, memory, and write back. And so what I can do now is, and there's one other simplification which we're doing, which is, for now we're going to ignore cases when we're doing branches or changing the PC to anything other than PC plus 4. And we're also going to take our register file and model it twice in this picture. So the one up here is for doing reads. The one down here is for doing writes. Okay? So using this new representation of my processor, I can pipeline it by just putting a register between each one of these stages. Okay? And so now I have my 5 pipeline stages, and assuming that there's no dependencies between them, this pipelined processor is going to work correctly. Okay? So let's take a look at an example. So suppose that I want to execute this sequence of instructions shown here. If I show this in a pipeline diagram, you basically see that the first instruction is the green low W. It comes down my pipeline diagram diagonally as we saw before, proceeding through each stage of my pipeline, which are where the 5 stages are: IF, decode, execute, memory, and write back. Okay? And then we have the next instruction, and so on and so forth. Now, if we take a look at when reads and writes happen in this pipeline processor, well, let's just analyze our first instruction, the load word. So the load word is trying to read X12. When is it reading X12? It's reading it in the decode stage, okay? So it's going to read the X12 register here in cycle 2, but it doesn't produce a result until it gets to the write back stage. So it's not going to actually write to X11 until the end of cycle 5. Okay, so this is what we're going to have to keep in mind when we continue with this discussion next time. So let's just conclude with one last example, which is, suppose that I now have a slightly more complicated sequence of instructions. In the previous sequence of instructions, there was no dependencies between any of the instructions because I was using different registers for every single piece. Now here, I do have a dependency. My add I is writing to X11, and my XOR is reading from X11. So now let's see what happens in my pipeline diagram. Again, if I draw it just as I did before with the instructions going through diagonally, I have a problem because my XOR wants to read X11 in cycle 3, but my add I is not writing X11 until cycle 5. So what does that mean? Is the XOR going to get the right value? No, the XOR is going to read a stale value. And so what we're going to do to solve this is we're going to introduce stalls. And so we're basically going to keep the XOR from reading its operands until we know that the add I actually was able to write. Okay? And so what's happening here is we're saying the XOR can't move out of decode until the add I is done with its writing. And so the problem with this, though, is that now I've introduced a whole bunch of what we call no-ops, which are no operation, which basically is saying that my cycles per instruction is not quite as good because I'm not completing an instruction every cycle. Okay? And I apologize for going over a little bit, and we'll continue with that in recitation tomorrow. Thank you.